In this video, we're going to take a look at section 8.4, testing a claim about a mean, and use the TI series calculator to run a hypothesis test about a mean. In this section, we're only going to take a look at cases where the standard deviation of the population is not known. So we use a student's t-distribution instead of a normal distribution. So the formal method of testing, here's our notation. N is sample size, x bar is our sample mean, and then mean of x bar is the population mean, and this value is taken from the claim and used in the statement of the null hypothesis. Requirements to perform this test is that our sample has to be a random sample, and either of the following conditions is satisfied. Either the population is normally distributed, or our sample size is greater than 30, or both. The test statistic is a t. This formula right here will be calculated by your calculator, and your test statistic will be given, so you won't have to actually calculate that statistic, but we could based on the values that we have. We would have the mean, the population mean, sample standard deviation, and square root of n. Again, we're going to use p-values because we're going to use technology. Alright, in this problem, when a plane crashed in Charlotte, North Carolina, 21 passengers were killed. In Lake George, New York, 20 passengers died when the Ethan Allen tour boat capsized. In Baltimore's Inner Harbor, 5 passengers died when a water taxi sank. In all of these fatal incidents, overloading was thought to be a contributing factor. Loading capacities were based on old estimates of the mean weight of men, but that mean has increased in recent years with the effect that some boats and airplanes have been overloaded and unsafe. Using the weights of the simple random sample of men from data set 1 in our textbook, we obtain these sample statistics. We have n equals 40 men, the sample mean x bar is 182.9 pounds, and sample standard deviation s 40.8 pounds. The original weights are in kilograms, and they're converted to pounds before computing the statistics. Use these results to test the claim that men have a mean weight greater than 166.3 pounds, which was the weight in the National Transportation and Safety Board's recommendation. And we're going to use a 0.05 significance level. So first item we do is check and make sure requirements are met. This is a simple random sample because it was stated in the problem. And then our population is greater than 30, our sample size. So either or both of these conditions met. If it was not greater than 30, we would have to make a normal quantile plot and take a look at it to make sure it was normally distributed, just like we did for confidence intervals. All right, we're going to write our null and alternative hypotheses based on the statements in the problem. So our null hypothesis, we're testing a claim about a mean, and the mean is the National NTSB's claim of 163.3 pounds. That's the standard that they use. So we're going to say that the mean is equal to 166.3. The alternative, based on our sample of 182.9 pounds, that looks like it's greater than, and it also states test the claim that men have a mean weight greater than 166.3. So our alternative hypothesis is that the mean is greater than 166.3. Notice that in the hypotheses, our sample weight is not in there. The 182.9 is not in there. So we assume that the weights are 166.3, and then we check and see how unusual it would be to get a sample of 182.9. So that's how the hypothesis tests are run. We identify the significance level, and we were given a 0.05 in the problem. We're going to run the test using technology. The textbook goes through how to use the formula in a little bit more traditional way. So with our calculator, this is a t-test. So we turn it on, we click Stat, over to Tests, and this time we're going to run a t-test. Hit Enter. They'll ask you whether you have data in a list or whether you have statistics given from the problem. We're not given the raw data this time, so we choose Stats. Hit Enter, and then your choices down here for entering items is altered. First item is, what is the population mean? What is the claim? What is our null hypothesis? So this would be 166.3. So that's our claim. And then x bar and s of x are the mean and standard deviation of our sample. So our sample gave us a mean of 182.9. Our sample standard deviation was 40.8. And our sample size was 40. And the test that we're doing this time, take a look at your alternative hypothesis. Its mean is greater than 166.3, so that's what we choose on the calculator, greater than. So we arrow over there, hit enter, and then we're going to calculate. So here's what we're told. Our test is that the mean is greater than 166.3. Let me scroll down here to the results. The mean is our claim, we think the mean is 166 greater than 166.3. The test statistic of 2.573 means that our value that we got, the 182.9, the sample, is 2.573 standard deviations away from the mean, okay, on this t-distribution. The p-value is 0.007 if we round it. This is the probability that if the mean really were 166.3, it's the probability that our sample would be 182.9. So in probability, that's unusual. So we pick that factor where it's unusual. Anything less than a 0.05 is unusual. And that's why we have a significance level of 0.05. It just restates our x bar, our s, and our n. Okay, then I'm going to go back to the menu for t-test and draw a picture of what we just did. There's our t-test. So when you go down to the very bottom, select draw. So here's what our curve looks like. It means that if the mean really was right here at 166.3, our sample landed 2.5732 as a t-score, that many standard deviations from the mean. And the probability of that happening, if the mean really was 166.3, the probability of getting a sample that large has a 0.007. It's less than 1% of getting it. So what we say is, our conclusion, the p-value is less than the significance level, a lot less actually. This means we reject the null hypothesis. It's customary to include the p-value in the conclusion so the reader can make his or her own conclusion based on your value. So here's our statement. There is strong evidence from our sample to suggest that the mean weight of men is greater than the claim of 166.3 pounds, with a p-value of 0.007. Again, notice that our statements are all based on our hypothesis, null hypothesis. We don't actually put the sample in there, the 182.9. We just say that it's greater than, based on the sample that we have. All right, so let's look at confidence interval in this case as well, since we can calculate those really quick on a calculator as well. It says run a confidence interval using the calculator and the sample values. Since this is a one-tailed test and we had a significance level of 0.05, we use a confidence level of 90%. So the one-tailed test is 5% on one side, but remember that a confidence interval gives you the middle. So we have to accommodate for that and have an area in the left tail of 5 for confidence of 90. So we go to, this is from section 7.3. We go over to edit, or stat, over to tests, arrow down until you get a t-interval. There it is, option 8. We have statistics again. Your calculator keeps track of what we've got, so the mean, standard deviation, and n are still there. But we need to make an adjustment this time and make that a confidence level of 90%. Again, we have a one-tailed test and we have 5% in one tail, so we need 5% in the other for a confidence, and that's 90% total. Calculate, and notice we get an interval of between 172.03 and 193.77 pounds. So our interpretation is we're 90% confident that the mean weight of men is between 172.03 and 193.77 pounds based on our sample of 40 males. The mean weight of 166.3 used by the NTSB is not in our interval. It's less than our interval. So the confidence interval supports that claim that the mean weight of males is greater than 166.3. So we're looking at the confidence interval as looking at our sample and trying to predict the population based on it. And then the population is not within, it just supports our claim, it supports our conclusion from our hypothesis test.